are in Unit 1, 1.7, so it's our last little section before our first unit test. Okay, does it make sense to talk about adding infinitely many numbers? So you might think it's impossible because it would take an infinite amount of time. Okay, but there are situations in which implicity use infinite sums. For instance, the decimal notation of the symbol 0.4 repeating means it's going on forever. We know that. Okay, but at the same time, it also has a value. Okay, 0.4 repeating is 4 over 9. So it's not, I guess, stupid. It's not stupid to actually figure out what that would be in terms of a limit, because it could be approaching a certain number, like 4 over 9. Okay, so kind of building on that, another idea is kind of a paradox here. It's called Zeno's paradox. Is that if a guy was walking towards a wall and he kept getting a half distance closer to the wall every time, well, technically he'd never get there if we want to be technical, but what would it approach? He'd approach getting to the wall, which would be 1, right? So it's like his would be 1/2, 1/4, 1/8, 1/6, etc. That would just keep going on forever, and you can kind of see those sums go 0.5, the half, 3/4, 0.875, 0.93, and then it continues to get closer and closer to 1. So in our limit world, it's approaching 1 still. Okay, so the idea is, you got to see again, they get closer and closer. So the idea is just understanding that these infinite sums can still approach certain numbers, which we can use limits to find what they are approaching. Okay? All right. Okay, so it just says, notice as we add more and more terms, the partial sums becomes closer and closer to 1. In fact, by making n large enough, that is, by adding sufficiently many terms to the series, we can make the partial sum as close as we like to the number 1. Therefore, it's reasonable to say that the sum of the infinite series is 1, because it's approaching. So then this will be the notation here. This might be something you want to write down. So limit as n approaches infinity. So now we're talking about approaching infinity, which means if we just kept going forever, what would it eventually get to? In this case, eventually he'd hit the wall, if we want to be technical. Okay? Okay, and we use a similar idea to determine whether or not a general series of terms, t sub 1, t sub 2, to t sub n, okay, has a sum. Okay, we define the partial sum as follows. So these are partial sums. So sum of the series are just, if you'd add sum of 1 would be just term 1, sum of 2 would be 1 plus 2, sum of 3 would be 1 plus 2 plus 3, etc. You're adding all the terms up to that number. Okay, so that's why S sub n here. This is kind of a general one. If you like writing down the definitions, that's kind of the general sum rule. And that should be something you do know from Math 20, I hope, if I serviced you well. Okay, in the infinite sequence, series 1 plus series 2 and series sub n of a partial sum of the series t1, t2, etc. has a limit L. Then we say the sum of the series is L and we write it. So if this is adding up, or it's, remember, do we remember the two words that we use for the patterns? Like they're either, what's that? Close, not repeating. Huh? Nope, but close. You guys are doing words. You have two types of series. You have a series that just takes off, and you have a series that like melts down to one thing. It's called convergent and divergent. Okay, divergent is your ones that take off. Okay, divergent is your one that take off, like one that just keeps getting massive. Like if I was timesing by 2, that's when it gets so big and it's going to take off. Okay, I'm not really going to. It's not getting to a number, so it's not going to have a limit. Okay, but if I'm converging to 0, okay, getting smaller, or like the one we just did was converging to what? To 1, right? So I'd be converging to a single number. Okay, so those are the ideas to think about. If you understand divergent, convergent, these limits will be pretty easy. Okay, all right. So if one is divergent, you can't figure out what the limit is? Right, because it's not approaching anything; it's just taking off infinitely. Yeah. Okay. Right, it could just dive. Right. Okay, in sigma notation, this looks like, so in sigma notation, we'll kind of get more into sigma notation later, but this is what it looks like. So what this means is if n equals 1 and we go to infinity of the terms, that would give us our limit. You use sigma notation for sums. This guy right here means to find the sum. Okay, if a series has a sum, it's called a convergent series. So if it has a sum, it's convergent. If it does not, it's called divergent, which makes sense because if it keeps getting massive, like she said, it keeps taking off, I'm going to be adding forever. It's going to be infinite. Like I'm never going to a number. But if it is convergent, we can say it's approaching 1, okay, or it's approaching 0, okay. So that's kind of what we were just talking about, convergent and divergent. Okay, and so that's kind of the idea today. Any questions on convergent, divergent, anything of that nature? Okay, I'll let you get this. This is kind of the main definition there. I'll let you write that down, and then we'll start into example 1. The sigma notation, sure. Just say this means this. Well, sigma means sum, so this is just for like a sum of a series. Up here? That's infinity. Yeah, sorry. This is infinity. That right there is an infinity symbol. Good question. Board's a little dirty. Okay. We good? Okay. All right, so example 1, determine whether the following series are convergent or divergent. Okay, so we're looking at A and B. So A. So it keeps going up 1, 1, 1, 1 forever. Okay, so if we looked at that limit, it'd be limit as n goes to infinity, and it would just be of n, because whatever term number is going to be what the sum is. Do we see that? Like here's term 1, the sum is 1. Term 2, the sum is 2. Term 3, it's 3, etc. You keep adding them. Okay, so this one would be does not exist because it is not. It's divergent. That's why, because it's going to keep getting bigger forever. We won't ever stop it. Okay, B, what keeps happening with B? We've done one of these before. So what are my sum? What's my sums going to look like? What's S of 1, S of 2, S of 3, S of 4 of B? So what's S of 1? 1. What's S of 2? 0. S of 3. And back to 0, right? So it keeps going 1, 0, 1, 0. So is it approaching anything? No, it's not. So again, this is a does not exist, okay, and it's going to be infinite, or excuse me, not infinite, divergent. No limit exists, divergent. Okay, example 2. All right, so example 2, find the sum of the geometric series. So geometric means, remember geometric was multiplication, okay, arithmetic was adding. Okay, so when it exists, so A plus AR2, etc. So we want to define this pattern, and I think, yeah, we'll get to it in a second. But we will define this as the sum would be, and this comes from your formula we used. So remember R was the ratio, okay, the ratio growth, so however it's growing. A is your first term. Okay, so this is general form. That's why you probably don't like it. There's no numbers. but R stands for the change. Like, is it times something by 2? Is it 1/2? Okay, A is whatever our starting number is. Let's get a better A here. This is not, oh no, too big of a eraser. Can I do, there we go. There we go. All right. Okay, so what we're going to do is we're going to look at different cases here. Let me, just one second, guys, hold on. All right, so we're going to look at 4 different cases here. So the first case we're going to look at is when R is less than 1, the absolute value of R. Okay, so the absolute value of R is less than 1. That pretty much means what? Sure, can be less than 1, yeah, or it also is talking about fractions, like 1/2 and etc. So if I put in, let's just use 1/2 for example. Okay, if I put that in, what did we learn yesterday about fractions under 1? They're going to an exponent. They keep growing. What happens to this 1/2 over time? Ends up being 0, right? 1/2, 1/4, 1/8, 1/16. It keeps getting smaller and smaller and smaller. Where when we take the limit of it, it ends up being 0. So then that would be A times 1 minus 0. This is by 1.6. Okay. All over 1 minus R, which essentially 1 minus 0 is just 1. And so if you might remember this, this is A over 1 minus R. We could use that. The only time that we can find, okay, the only time we could find series of geometric is when they had to be between this restrictions. Because what if my R is 2? What happens then? What happens when my R is 2? So what I'm telling you is this is a specific example or specific R's that we can actually find the series of, the infinite series of. But if it was bigger than 1, if I said 2, why could I not find that infinite sum? Yeah. It will give us, on this example, yes, on this example it will give us negative. Well, nope, it'll give us negative over negative, so it'll actually give us positive. Right. The problem is this guy, if it was 2, as we kept getting bigger, it keeps getting massive. It does not ever converge. It diverges. Okay, so that's the problem. The problem is that it would not be, and we're going to talk about the next cases here, so I'm kind of getting ahead of myself. But the point is, this, you hopefully recognize this a little bit. We use this in Math 20 to find what infinite series were if it was convergent. Okay, that was kind of your rule to use it. Okay, let me erase this here. And then I'll do case 2. Okay, for case 2, they're going to assume that R is 1. And if that happens, then you're going to get essentially the limit's not going to exist. Because actually what will happen is you'll end up getting A1, A2, A3, A4, and it won't be convergent. It'll keep going. Okay, or you could also see you have 0 over 0. So if you use R equals 1, the limit won't exist. Okay, when the limit doesn't exist and it's not approaching anything, therefore it would be divergent in our eyes. Okay, and while you're writing that, case 3 is the converse of that. If R was negative 1, the series again would go back and forth between A, negative A, negative A, and it would not have anything, it wouldn't be converging to anything again, so the limit would not exist again. That's why absolute value of R less than 1, not less than equal to. Okay, and then we already talked about case 4, so when I jumped the gun on, case 4 is if R is greater than 1. So like we said, 2, the limit will not exist because it takes off. I put that for infinite instead of writing infinite. Okay, it gets infinitely bigger. Okay, it just keeps getting massive. Those are kind of our different cases when we're addressing those. All right, so in summary, what we want to get from this is, if R is less than 1, then it is convergent. If your absolute value of R is less than 1, it's convergent, and we can find the limit. If it's not, then we cannot, because the limit will not exist. That's the summary. Okay, and we just got 2 quick examples here, and then we should be done. We good? Oh, sorry. Oh, you're good. No problem. Okay. All right. So, example 3, find the sum of the series, okay, of the infinite series. So, first off, we get the first term. We know our A, remember A's first term is 16. Okay, when we try to figure out what the common ratio is, what's our, how do we figure out what R is? Remember, from Math 20, how do you figure out what R is? What's that? Can I say it again? Yeah, this one's going down. Close. For common ratio, it's term 2 divided by term 1. Because it's a geometric, so we divide. You were kind of talking about arithmetic. So this would be -3/4. -3/4 is my common ratio. So let's see if we learn anything in the last 5 minutes. Is this a convergent or divergent series? Oh, convergent. Oh, okay, it's a 3. Fair enough. Absolute value of 3/4, is that less than 1? Yes, because 3/4 is less than 1. So this is a convergent series. Okay, so we can find the sum here because it is converging. Okay. So since it is, we can use the formula. Now it's just formula work. It's going to be sum is A over 1 minus R, which our R is a -3/4. That's all we have to do. All I'm using is this formula here. S equals A over 1 minus R. So that gives me 16 over 1 3/4, which if I change that all the way to fraction, that would be 7/4. Okay, and when we get that done here, we would get 64/7 is this answer for the sum of the series. Okay, again, if you don't see that, if you're still struggling with your fraction, 16 divided by 7/4 is 16 times 4/7. 16 times 4 is 64/7. Okay, and I think the next one's interesting. To me it is. We'll see if you guys care. Alright, so for example 4, we can, by knowing this, we can figure out what this decimal is a fraction without just using our calculator and hitting the fraction button. Okay, so example 4, we express the repeating decimal 2.135 as a fraction. Now the 1's not repeating, okay, so don't think that. So what you do is you're going to break this up into knowing it's 2.1 and then it's 35, 35, 35, 35, etc. That's essentially how we're going to break it up. We're going to really focus on the repeating part. Okay? So how I write this as a ratio, or excuse me, not a ratio, a series, would be 2.1 plus, now what place value are these ones in? Yeah, so it's 2.1, so here's my tens. What's this? What's after your tens? Hundredths and thousands, right? So this is 35 over 1,000. That's how you demonstrate that as a fraction. Okay, so if this is 1,000, what's this one? 10,000, 100,000, right? We're getting used to it. So this would be 35 over 100,000. Okay, and the last one, just for fun, would be 10 million. It'd be 1 million, 10 millions. And that would just keep going. So what we can do is, we want to figure out what A is still. Or excuse me, not what A is, what R is. Okay, excuse me. So we're going to start, and you can do this, you can always manipulate where you want to start your terms at and whatnot. We're going to start right here for our first term to figure out what the R is, because the pattern doesn't start until after 2.1, so this guy's just kind of hanging out. He's just kind of waiting because he's not part of the pattern. So what we're going to do is we're going to call this term 1 and this term 2, and you're going to go 35 over, we're going to go 35 over 100,000 over 35 over 1,000. So essentially, again, remember, when you do a divided fraction, this goes to the top, this goes to the bottom. Essentially, the 35s cancel. You're getting 1,000 over 100,000. The 10,000. Yeah, the 10,000th place is right here. So we're going by 2. So this is the thousandths place. So here's tenths, hundredths, thousandths, 10,000th, 100,000. So since we're stopping every 2, this one's in the 100,000s. We're going like every second number. Okay. Yes, yeah. And so second term over first term, this gives me 0.01 is my R. Now does that work for our, is 0.01 less than 1? Yes, so this is another convergent graph. Okay, it's convergent. Okay, and with that, we will use, we will go ahead and use this here. So we're going to go 35, we're just keeping this our term 1. We're going to go, because it's A over 1 minus R, so we're going to go 35 over 1,000. That's my A, term 1. Because again, we're kind of setting the 2.1 aside because it's not a part of the pattern. Over 1 minus R, which is 0.01. Okay, when you do this into your calculator, you're going to get 2.1, we're going to go, because the 2.1 we're going to bring back in a second, plus 35 over 1,000 times 0.99. That comes from, the 1,000 essentially just jumps down here. Okay, 1,000 times 0.99, the 0.99 comes from doing this operation here. Okay, so if I write this as a fraction, what's 2.1 as a fraction? How can we write that as a fraction? (21 over 10), not 2 and 1/10, 21 over 10. 21 tenths is 2.1, right? Okay, and we're going to add that. This works out to be 35 over 990. Because 0.99 times 1,000 is 990. And so what we're going to do is, we're going to do common, like we're doing this out calculator. I mean, you can use calculator for the multiplication part, but we went ahead and made these into both 990s. And you end up getting 2114 over 990, which reduces to 1057 over 495. So I know it's kind of some not so fun fraction work, but 1057 over 495 is that decimal we have. Okay, where did I lose you, Jeremy? Oh, sorry. Which one?
The 2114 over
490. Nope, 990. Sorry, 990 equals 1057 over 495. And then if you put that, what's that? Oh, yeah, it does. Lost. I'm lost with my handwriting. Okay, if 495. Yeah, half of this. I know, because I'm like, I cuff myself. And so as I get lower, I can't really steady my hands. I'm like old man syndrome. Okay, when you put this in to your calculator, the cool thing is it equals this. So you just figured out that 2.135 repeating is 1057 over 495 as a fraction. Is it correct, Rachel? Is it good? All that. Right. If it's not convergent, you can't use formula because you can't find a sum of a non-convergent, of a divergent series. Okay?